Today, we want to continue thinking about integration and then move on to the big idea that's going to drive a lot of the mechanics in this class. One of the big questions of calculus is to figure out what's the area under a curve and above an interval. We know this to be the definite integral from a to b of f of x dx, but we want to remind ourselves where this comes from. The big idea is that we're doing multiplication, but one of our factors is continuously variable. If we think about area as length times height, area, length times width. If the length is constant, then we get to use multiplication. If the length is variable, but not continuously so, then we just use a bunch of addition. We do any length times width when we can, and then just put plus signs in between all those areas. But when our length is continuously variable, that's when we have to integrate. This is one of the things that integration is for. Integration is multiplication, but one of the factors is continuously variable. The variable part isn't a big deal. We just drop back to addition. The continuously variable part is why we're in this class. It's that continuum that we have to deal with. There's nowhere to put the plus signs. How are we supposed to add? And that's where calculus enters the chat. So integration is addition. The thinking was, we flatten out the curve in short bursts. So that f at xi is us flatten out the curve in short bursts. I'm writing in the space that I need. If we look close enough, everything is flat. We look out on a big field and we say that field is flat. It is not, it is curved. We look out on the surface of a still lake and say, look how flat the water is. The water is not flat, it is curved. We're just looking at it very closely. We're too close to see how curved it is. Or we could say that if it's a small enough lake, the lake is too small to really demonstrate enough curve. If you look close enough, everything is flat. If it's continuous, that's where the continuous requirement comes from. So we're going to flatten the curve in short bursts. Notice one of the things that we've introduced here when we flatten the curve is an indexing. This is where we drop out of the continuous into the discrete. Here we have index. We've chosen a bunch of values. Indexing means we're no longer continuous. So the indexing means we have a place to put the plus. Flattening the curve allows us to use multiplication, length times width. The indexing, doing this a bunch of times, allows us a place to put the pluses. We're now with our nice familiar addition. There's going to be a lot of these, so rather than putting A1 plus A2 plus A3 plus A4 and so on, we're just going to say add up all the A's. So we're going to have a big sigma here in a Riemann sum. And do this for all these n rectangles. So this is the sum as I goes from 1 to n. So this is f at x1, delta x, f at x2, f at x3, all the way up to f at xn. So n is the number of rectangles that are in play. So n is our number of rectangles. We know that increasing the number of rectangles will improve our approximation. So the calculus way is to do whatever's improving your calculation or your approximation forever. So this is just say use infinite rectangles. Whatever you're doing, do that forever. And this is where we run into the central tension of calculus, the discrete versus the continuous. If there's an infinite number of rectangles, if we divide something by infinity, doesn't that make it 0? No, it clearly does not, because if the width is 0, then the area is 0, but clearly there's some area there. That's why we're in the central tension. That's why we're in the weirdness. Similarly to the problem we ran into with the secant lines and tangent lines. Delta y over delta x is all good and fine when there's 2 points, but when there's 1 point, we're looking at 0 over 0, which is undefined. So we have to know which 0 over 0 we're talking about. Welcome to the weirdness of infinity. Fortunately, we don't leave anybody hanging too long. This Riemann sum we know becomes the definite integral. That dx we're thinking of as being the width, which is very small and close to 0, but is not 0 because multiplying by 0 would make everything 0. And f of x, now without the indexing, is our continuously variable length. The weird thing is, instead of taking the limit as n goes to infinity of the sum of all these rectangles, we are now writing this definite integral notation, the integral from a to b. This part of the integral is telling us everything that we should plug into the expression f of x dx. That's the place. That's all the x values. We're going to evaluate the expression f of x dx. So here's our discrete number of rectangles, and here's our continuum that we're plugging into the expression f of x dx. So the Riemann sum, thus looking at this as a discrete problem. Our definite integral is where we have our continuous problem. Now, once again, we also don't keep you hanging very long on this definite integral business because we have ways of calculating the definite integral. And our favorite way is going to be to use a machine like a calculator. Wait, no, that's not it. We're going to use the fundamental theorem of calculus. That's what comes in and helps us with this expression here. So this expression here, according to the fundamental theorem of calculus, is capital F at B minus capital F at A, where capital F is an antiderivative of little f. And that's our fundamental theorem of calculus. Any questions? What I wanted to review here is the thinking behind our integral and the way that we read the integral. We want to evaluate this expression f of x dx at all these x values, the interval from a to b. The reason that we want to read this integral expression is that this integral expression, how to read this expression, is consistent when you move forward to other things. So part 1A, DVD bonus video. This is going to get cut from the full release, but on the DVD bonus bonus materials, this is going to be one of the deleted scenes, and they'll be in the director's cut. And it'll be director's commentary, which is just me talking over myself. It's like double leech, really annoying. It's like, that's why no one buys it. You can also only purchase it in my imagination, and that's why it's not available to the public. In your future, you have multivariable calculus and vector calculus. Some of you be like thinking it's like, oh, I'm going to skip Calc 3. I don't need it for my major. To which I'm like, oh, that's okay. I like not knowing stuff too. Wait, no, opposite of that. In your future, we're going to talk about multivariable calculus and vector calculus, and we're going to be integrating a lot of stuff. The thinking is going to be the same. The way we read what the integral is about is all the same. So this is a double integral. It's a double integral because our function is of two variables. A function of two variables is not going to represent a one-dimensional curve in two-dimensional space. A function of two variables is going to give us a two-dimensional surface in three-dimensional space. So a function of two variables is a two-dimensional surface in three-dimensional space. We're going to interpret the integral the same way, but we're going to have to update to these higher dimensions. The integral of a function of one variable is the area under the curve and above an interval. But if we have a surface, we're not talking about an area. We've got an area on the top. What we're talking about underneath is a volume. So the surface might be the ceiling. And I want the volume under the ceiling and above the floor. And here, this R, that's the floor. So this double integral represents the volume under the surface There's our three dimensions, X, Y, and Z. And above the region R, we just increase everything by one dimension. Instead of an area, we got a volume. Instead of one-dimensional curve, we got a two-dimensional surface. And our double integral is telling us the same thing. How much space, how much stuff is under the curve or under the function and above the plane, the set of inputs. And that integral is telling us the same thing. The integral over R, this part right here, is telling us what we're plugging into this expression, f of x, y, dA. dA is a little square of area on the floor, just like delta x or dx is a little piece of our interval. So that dA is some small rectangle of area in the region R. The calculation that we're making here, f of x, y, would be the height and dA is the area. So the calculation that we're making here is that volume is equal to the height times the area. That integral over R, that's just telling you what values of x and y to plug into the expression. We plug in values of x and y into the expression f of x, y times dA. That gives us a little piece of the volume. We just add up all those volumes because integration is addition. Because integration is multiplication, but one of the factors is the way we interpret this notation is the same that we're using now. But right now, it's hard to see why we would want to think about this, interpreting it in this way. Mainly because our stuff is too simple. All we have is a one-dimensional curve in two-dimensional space. Above is the curve, below could be, the only fancy thing would be to make it another curve, in which case we just subtract anyway. No big deal. Any questions? So, back to the single variable version. Note that we're using area is equal to length times width, but this works for anything, any multiplication. Any applications of multiplication are now applications of integration. We take anything that we use to multiply, make one of the factors continuously variable, and now you've got another application of integration. Our favorite is area is equal to length times width. Distance is equal to rate times time. we just make our rate continuously variable. If our rate is constant, we get to multiply, but if our rate is continuously variable, integration problem. Other favorites, work is equal to force times distance. If the force is constant over the distance, then all we have to do is multiply. Life is easy. If the force is variable over the distance, then we have to integrate. If the force is continuously variable over the distance, then we got to integrate. I'm going to do this AM Gold style, plus many more. Rather than learning the particular application, learn what integration is for. Integration is multiplication, but one of the factors is continuously variable. Is everybody okay? Eventually, I'm going to have to explain things like work is equal to force times distance, or force is equal to pressure times area, all this stuff. And this is one of the reasons it's good to have the class way out here in building 4, so I'm far away from my physics colleagues. So my physics colleagues don't have to watch me try to explain physics. And I have to worry, like, if you can tell I'm going to do a physics problem, because I like walk to the door and check. You know, physics colleague down here, then I close the door and then I walk back. All right, we're going to do a physics problem. I better turn off the recording. Otherwise, I'll be sitting in my office, happy in my lack of ability to explain physics, knock on the door, and the whole physics department's out there. We have words. Oh, no, and then I jump out the window. This is why also I needed an office with a window. Now the window doesn't open. So this is why I keep a fireman's axe in my office. It's not for the upcoming zombie apocalypse. It's like, uh-oh. And then like I look behind them and chemistry is like, oh, yeah, we got next. I go, uh-oh. And I grab the axe, I just break out the window and I jump out. I haven't had to do that yet, so. All right, what are we talking about? Oh, yes. One side note, super short video, set it to less than a minute. I think I do this in less than a minute. The great news is that integration, go back up here, integration is multiplication when one of the factors is continuously variable. Integration works just fine if your function is constant. It works exactly the same. So, perfect. How's everybody, okay? Everybody looks stunned, y'all look at me. It's an 8 o'clock class, and some of you are just now realizing what this means. Oh, wow, this is not just a temporary thing. I've got to get up and be here at 8 o'clock, 4 days a week for the next 17 weeks. You chose this, so don't be all mad at me. You picked it, all right? You thought it was a good idea. If you'd asked me beforehand, it's like, oh, dude, no. Like through my class last semester when it was at noon. It's like, well, hey, I was thinking of taking your Calc 2 class next semester. I'm like, oh, dude, it's at 8 o'clock. What are you thinking? And you might be like, oh, well, they're paying me to be here. Right? So it's kind of an easy decision for me. It's like, oh, I don't know if I want to do 8 o'clock. It's like, oh, well, we're going to pay you to do 8 o'clock. I'm like, oh, fuck yeah, 8 o'clock. I'll be there. Bright-eyed, a bushy tail, and highly caffeinated. Not caffeinated enough yet. But y'all, I don't know. Some of you might be morning people. I don't know. It's hard to tell. Because even morning people that are bright-eyed and bushy-tailed, they walk into a math class, it's just like, right, sucks all that energy right out of you. Crap, it's math. How did you know my one weakness? Don't use the wrong pens on your rocket book. And if you do, don't be stubborn about it. It's like, oh, maybe there's just something wrong with this page, because you'll end up ruining 2 pages of your rocket book. All right. So we just brought it up. So let's move on to our next video. The fundamental theorem of calculus. Let's write it down so it just shows up on the video. We need to talk about the fundamental theorem of calculus. Both versions of the fundamental theorem of calculus. We got 2. One thing to note is that the fundamental theorem of calculus has a whole sentence. There's some if and there's some then. And the theorem only works if you have both parts. So first of all, there's the setup. What is this theorem about? So we're going to say let f be continuous on the closed interval from A to B. And let C be an element of that interval. This is the setup. This is where we set up what we need for this theorem. This theorem does not work if the function is not continuous on a closed interval. There are 2 parts to our fundamental theorem of calculus. And it's cool because it involves 2 elements. And it's just that this goes both ways. First part. The definite integral from A to B of f of x dx is capital F at B minus capital F at A, where capital F is an antiderivative of f. That is, the derivative of capital F is little f. In this textbook, this is the first part of the fundamental theorem of calculus. If you want to state the first part of the fundamental calculus, you first have to tell us what we're dealing with, and then you have to tell us what you want to conclude. It involves all of this. You can kind of leave off this part. You can just say capital F is an antiderivative of little f. What this part of the fundamental theorem of calculus says is that you can calculate a definite integral using an antiderivative. You can use an antiderivative to calculate a definite integral. That's what we're saying here. Use an antiderivative to calculate a definite integral. So good news. That addition over a continuum can be dealt with this derivative. This is how we add up over a continuum. There's nowhere to put the plus, so we're gonna have to use some antiderivatives, then we can calculate our definite integral. Right. There's another part. If you define the function capital F of x as the definite integral from c to x of f of t dt, the function defined this way. Now, this is the second part. We don't just get to suppose that there's an antiderivative. In the first part of the fundamental theorem of calculus says, like, oh, well, you can do this definite integral with an antiderivative. Raises the question, what if there ain't no antiderivative? What then? Enter the second part of the fundamental theorem of calculus that says capital F of x, defined to be the definite integral from c to x of f of t dt, is an antiderivative of little f. So what we get from this is that we can use a definite integral to construct an antiderivative. We can use a definite integral to construct an antiderivative. The reason that this is excellent is that the definite integral can always be approximated, for a continuous function anyway. A definite integral can be approximated to any degree of accuracy with just area. We can always approximate a definite integral just by calculating area with enough data and calculating power. We can do this to any degree of accuracy. This is important because using an antiderivative to calculate a definite integral is naturally very limiting because it requires us to find antiderivatives. And this, we know, can get messy. And by messy, I mean become impossible with finite combinations of elementary functions. So here are the two parts of our fundamental theorems of calculus. The summary is we can use an antiderivative to calculate a definite integral, and also we can use a definite integral to construct an antiderivative. The two things go together. Important thing to realize that this is, we always say, the fundamental theorem of calculus until you get to top 3. And you find out that fundamental theorems of calculus are like skywalkers. There's always another. Any questions? Comments? I'll bring up the skywalkers because I took, well, Alex, I'll take things that don't make no sense in the Star Wars universe for $800. I usually take this opportunity to hack on J.J. Abrams for a little while. If you like J.J. Abrams' work, that's okay. You're wrong, but I mean, no, I'm just kidding. You can like stuff. Someone got to tell J.J. Abrams, it's fine to have a mystery box, but the author needs to know what the F is in it. The audience doesn't need to know what's in it. The author needs to know what's in it. Otherwise, you're just making shit up. You know what I mean? Otherwise, your story ain't gonna make no sense. Like, none at all. Incidentally, I do like making fun of J.J. Abrams. The primary thing that ruined Star Wars was Star Wars fans. Star Wars fans are the worst. What happens when The Force Awakens comes out? Everybody's like, it's just like the first one. It's just redoing the first one. What happens when Last Jedi tries to do something different? Oh, it's too different. What's going on? It's not Star Wars. The proper response to people that like or don't like these movies is like, oh, fuck off. Get over yourself. Star Wars has been ruined for a very, very long time. You know what I mean? There are certain things that should be taken away from certain people. And I'm thinking about Star Wars and Star Wars fans, including George Lucas. But the problem is we're just way too late to take it away from George Lucas. Like, oh, they sold it to Disney, but like 20 years too late. It needed to go away before Special Edition. Does anybody remember Special Editions? These are movies that are older than you. I have not watched all the new shows. I've heard Andor is awesome, so I'm looking forward to that. I super enjoyed The Mandalorian. And until The Mandalorian came along, the best Star Wars thing was the old Knights of the Old Republic video game. What would have made a better prequel is to just have a camera watching some dude play Knights of the Old Republic. That would have made a better movie. All right. That's going to do it for today. Think about these fundamental theorems of calculus, remind ourselves what this means, and tomorrow we'll busy ourselves with the idea and the skill of finding these antiderivatives. That's it for today. I'll see you all on Monday. No meeting tomorrow, just office hours. Everybody have a good weekend, and thanks for playing.